So, I have no microphone. I have a tie today, so it's easy for the microphone, no?
Yeah.
It's okay?
Can you hear?
Can you hear, please? Yeah? Okay.
And then you know how to operate this.
Yeah, no, normally.
Other.
Next. Normally it should work.
Here.
Yeah, it's here.
Other side.
It's other side.
Yes. That's forward. Just
Yeah, okay, fine.
No, yeah.
Okay. Good afternoon, yes. Today we will speak about cold nuclear transmutation. My intervention is based in two sections. First of all, inter-alpha particle bond structure for an alpha nuclei, and second part is concerns the other ones. So on the first part, several authors predict actually that alpha particle structures should be present in atomic nuclei. And there are some convincing arguments for such structure, which are provided by systematics of binding energy in the even nuclei with equal number of proton and neutron. So for me, a first point to consider concerns the binding energy of alpha particle and its relationship with those of deuterium, tritium, and helium-3, which are nuclei pre-existing to that one of helium-4. Why? Because it could be interesting to see if there is a relationship, even if it's completely different. So a second point is to see how these three binding energies play a role in the bonds between the alpha particles, because if they are alpha particles, basically there are also bonds between these alpha particles in order to hold them together. So my aim today is to show to you that according to my theory, the nuclei of the various elements are constituted with alpha particles mainly, other nucleons also, and that they are bound together by some bonds of type deuterium, NP I call to be more rapid, tritium, NNP, helium-3, NPP, and one NN, which is a new one I have to introduce. I will explain you. These are linked, all the three are linked by the little equations you see at the end of that slide. I skipped some slides because we have to go a bit quicker, I think. Two remarks before beginning. Geometric structure of atomic nuclei. I do not actually address this point, you see. I go that for Norman Cook's model, which is for me fundamentally good. Nevertheless, bonds are not equal in the nucleus. And so there is a tendency to group some nuclei in certain clusters. And also, second point, it's very important to know the distribution of the binding energy of each element at the beginning of the reaction of LENR and at the end in order to see what has changed. This I will try to show to you. Actually, my idea is to trace what happened in the reaction. So binding energy of alpha particle. The first part is part of my theory, of a larger theory. I cannot go in because it would be too long. What is to notice is that the binding energy for alpha is equal to these four binding energies. The first one, the NN, which is new. I have a little bit to introduce. The others are exactly those concerning deuterium, tritium, and helium-3, actually. So I demonstrate in other documents that this 2NN element is actually a d neutron and this has to be taken into account for the binding energy. Of course, I cannot sell this you like that. I have to question the validity of that model. The model is first based on Linus Pauling idea, relatively old idea, saying there are some clusters within the nucleus. And second, to present the validity or to assure the validity of that model, I try with about 200 nuclei to see how it works. So it works, and I have just issued a book. I have issued a book which can be downloaded because I gave the link to our organizers. So if one is interested, he could have it for free. So now look a little bit at the structure of the nuclei. Yeah, first one. This is oxygen 16. It's relatively easy. You can see, just a moment, here, that we have 4 alpha particles, according to my theory, which are bound by this 2Nn and by 2Np, 2 deuterium 1s. I group them because I noticed that they come very often and they are actually competing. So I made of that what I called A bond, which is very, very solid because everybody knows that the oxygen 16 is a very solid bond. So these 4 alpha particles, as said in the little thing there, 4 alpha beta are linked with these 4 A bonds. A bond is equal to Nn half plus Np half bonds. And within an A bond, the Nn and the Np bond are constantly alternating, oscillating, actually. And this alternative movement creates the most solid bonds. It's a reason why, for me, according to my theory, that the O16 is very solid. Next one, Ne20. You can see here that there are some modifications, actually, because this is an uneven alpha particle nucleus. It is often linked by a 3-dimensional system, here NPP, instead of a double one. So I could calculate the binding energy, which is quite good compared to the AM 2012 one, which are the latest, I think, issued values of the binding energies. So here, compared to O16, there are some modifications due to the effect of the introduction of 1 alpha particle more. The same with Mg24. You can see there are some modifications due to that. Again, the values are very good compared to the values of AM 2012. I just say, you see, I can calculate the binding energy very precisely with only a few parameters, Nn, Np, Nnp, and Npp, and of course the alpha. This is new, actually. The structure of my nuclei are not different to the normal structures. I do not address that structure. I address the bonding. It's a bit different. It's another angle of view. So, in this bonding, as you know, we have a lot of parameters always, sometimes 100 or 200 to calculate it. I do it with 4. And this is interesting, of course, we will see for LENR purposes. Next, SE28 is the same. I skip a little bit in order to go quicker. The most interesting one is that one, S32. you see here also the correlation with the value estimated or estimated value. Actually, there is a core structure which is equal to that one of oxygen 16, and the other alpha were put at 90 degrees. We can see it a bit better on the next slide, where we see that a tentative transmutation process of the two. If they are put at 90 degrees, they interact with 3 alpha particles. So NPP is privileged to the R1. And it's the reason why we have this structure. 2NN, 2NP is the structure of O16. 4NPP is the structure of typically the second O16, which is giving S32. That point is interesting because this morning George Egeli spoke about transmutation and especially also about that transmutation. And so I cannot say that my theory is the explanation. This would be pretentious, but it's perhaps an explanation we could discuss. Actually, it works, and it's very easy. So we turn on to the next. This is also interesting. It is 36, just a moment. 36, you can see here also that there is a structure equivalent to Na20, etc. They are all practically equal because, of course, they are bonded by 4 different bonds, only 4 different bonds, which are absolutely practically equal. This is a tentative transmutation also between Na20 structure and O16 structure. And you can see only one, was added actually, 3A and 1 NPP. And the result is quite good in comparison to the estimated value. This is the last of the several alphas. You can see also here the structure of CA40. CA40 is made of O16 and MJ24. You can see here the bonding of O16 and MJ24 and the bonding for CA40 is practically the same, with the exception of addition of 1 NPP in 1 NNP. So CA40 bonds represent O16 plus 20 MG24 with addition of 1 NNP and 1 NPP bond. So what we can say now as, let's say, conclusion of that first section, that according to the hypothesis I developed, the alpha particle, the nuclei are based on alpha particles with these kind of bonds. But we have to verify it with far more nuclei, of course. These bonds are very well known, except NN, you see. The NP is the deuterium, then the tritium, then the helium-3. And of course, they are how do you call that, coordinated through these equations. So now in the next section, I intend to see the kinship between 1 and alpha nucleus and its stable isotopes till the occurrence of the decay of neutron into proton, yielding the next element in the table. First, coming again to O16, I do not insist, you know now my theory. Now look at O17. O17, you can see that is a modification compared to O16. There are only 3A instead of 4. And instead of having the A here, we have NPP because one N has been added. It's an isotope. So it becomes NPP. And of course, we have also a very good correlation with the estimated value or the experimental value. So according to me, O17 is equal to O16 minus A plus NPP. Now looking O18, a second neutron was added. What happens? We have still the structure of O16 which appears. Two N's are added, and they are linked either by two NP ones or one NPP. I do a mix between both in order to create a symmetry. This is O18. So O18 is equal to O17 plus A plus 2NN, or equal to O16 plus NPP plus 2NP. Now more complex is fluor-19, because this is a new nucleus. It's not an isotope, but it could be considered actually as an isotope. But we can discuss that. It's not exactly, after our theory, an isotope, but it could be. A P was added because a proton was added. And you can see here the structure of O18, which is practically the same. We have added one A and two NP. So F19 is equal to O18 plus A plus 2 NP. This was the first series. You have a second series. Of course, in my book, I have all the series, so practically all the series, but I cannot present you all of them for reasons of time. I still have 8 minutes. So now we are going from Na20 to Na23. This is the structure of Na20. This is a varying figure, a varying drawing. It is the same in terms of value. Sorry, I went a bit quick. And it's now a turn of 22 or 21, but 21 we can skip for reasons of time. Let's say take 22. On 22, you can see that we have again this structure, which is the same, the N, and the addition of NP and NPP, etc. So the calculation is very easy. This is Na22. NR23 is quite interesting. You can see again that it's practically like an isotope of Na. I have modified a little bit the bonding, but the NPP could be here and here. And the P is bound by 2NP, etc. So actually, we can say that NR23 structure is equal to Na20 plus 6A, 4A for that, and 2NP, which are added. That's all. This shows quickly a certain kinship between the various nuclei. Of course, on 10 nuclei, it's not possible to base a theory. Nevertheless, I have calculated far more, 200, 300 ones, and it works. It's a beginning of a proof or beginning of a theory to be discussed, of course. I do not pretend having found something, but nevertheless, I pretend that we could perhaps dig a bit deeper on that point. It's a very easy point, and it's very important. I insist for LENR, because if you can trace all the nuclei, nucleus after nucleus, isotope after isotope, we can determine each time which has changed compared to the former one. And this is important. When knowing that, we have a far better knowledge than just to say, oh, nickel 62 has transformed in copper 63 according to let's say, just like that, you see. We can see the difference. Okay, now we have still 5 minutes for the questions. So please, some questions, if there are any. Yeah, okay. Come to the microphone, please.
No,
I'm not the moderator, but it's important to...
I can see how you can use this to calculate the total energy released from the first to the end of the run or something, but you imply that you can track things during the run, and I don't understand how you do that.
Yeah, okay. Basically, presented like that, it's difficult to understand. Of course, this is based on the theory of the neutron-proton I have developed many years ago, and which gives me the possibility to calculate all this very rapidly. I do not calculate it, of course, with the maths, etc. I calculate it according to a system, which is my cooking, of course. And this cooking allows to go very rapidly. In 5 minutes, I could calculate the binding energy of a nucleus. I can show you how, but of course then I need a blackboard or something because it's a bit difficult to do it as an Italian way. So, yeah. But you were first, George.
Yes. I always ask theoreticians whether their model has predictive capabilities or just postdictive. That is, you describe what is known, or can you give a helping hand to the experimentalist who, let's say, wants to make gold? This is just a rude example. Then if I want to make rude, what kind of materials to start to push them together, or whatever other materials? Does it have a predictive capability, or you are just able to describe what Mother Nature has already done?
No, it has a predictive, of course, according to the general theory, which I have not presented here. It has a predicted one, and it's also very close to the experimentalist you are, because you are a very good experimentalist. I know that from a lot of years. I know you, and think I want to help. You see, the people dealing with LENR, saying, okay, you have on the entrance one nucleus, and at the end you have another one. What happened? Very basically, what happened? It happens that some bonds have changed. The structure has changed, but the bonding has changed. The structure is very easy. If you say, okay, nickel 62 has transformed in copper 63, the structure is easy. It's a new structure. But why? Because of different bonding systems, etc. And this I can predict. Yes. I don't know if it's you or you were first, but we can speak also this evening, you know.
So in 1970, I believe, the Solvay conference, Symmetry Properties of Nuclei. In 1970, Solvay conference, Brussels. I believe that Solvay conference at that moment debated basically the same principle here. So helium nuclei bonding energy, as you calculate. Yeah. First question is that what you based your work on? And second question is, did you try other configurations, if you will, other nuclei or helium nuclei?
First of all, it's, of course, I based my work on that. Secondly, of course, I tried a lot. You see, it did not come from the moon or from the stars immediately. I tried many models, and I find that one. Sorry, we're now out of time, but maybe just a little questions and.
I was interested in this sodium-23 and also in your fluoride-19, why you don't have 5 alphas plus a tritium in this one, and in fluoride 4 alphas plus a tritium, but you divide up the N's and P's separately rather than making a tritium and hanging it out there, which I think would be probably more realistic.
Yeah, maybe it's possible to change. You have seen the equation I have at the beginning between NN, NP, NP, etc. So if you manipulate these equations, you can change things.
Okay.
Yeah, I can explain you that better before beer this
Right, and
evening.
are you familiar with what's known
Sorry?
as Ikeda diagrams?
Diagrams, yes, are not very nice, my diagrams. Actually, you see, I'm not I'm an old man. I'm not able to do a lot of colors with computers and these kind of things. But for me, the structure is not so important. For me, the structure of Norman Cook is good. You see, what we had to add is the bonding. So I put into consideration more the bonding here than the structure. Okay.
Thank you.
Yes, as I've discussed this with Philippe in the past, I think the bonding that George was suggesting as being contributing to understanding LENR reactions is key, and particularly if there are any frequencies associated with that bonding that cause things to happen with impulses of energy of some sort. And Philippe hasn't really alluded to his theory about protons made up of electrons and protons, positrons, but I think that's key because it suggests an electric magnetic coupling in the proton, which suggests dipole interactions at a short scale and so forth. So I think that development is key in the sense that George suggests as being important in understanding LENR reactions, frankly.
Thank you. It's not a question, it's a nice comment. Okay. Thank you, Bob. Okay.